All right. Hello and welcome everybody to Georgia Tech Graph Theory Seminar. Our speaker today is Taísa Martins from Fluminense Federal University, and she will tell us about weak saturation number of complete bipartite graph.
Thank you, Anton, for the invitation to give this talk. It's a pleasure to give the talk. So, can you hear me fine, right? I think you can. Okay. So today I'll be talking about the weak saturation number of complete bipartite graphs, and this is a joint work with Kronenberg and Natasha Morrison. So before we start talking about defining what is the weak saturation number, let's see what is the saturation number. So given graphs F and H, suppose that you're given a spanning subgraph of F. We say that this spanning subgraph is FH saturated if there is no copy of H in G, but whenever we add any edge to G, there is a copy, we create a copy of H. So for example, K23 and C5, they are all spanning graphs of K5. And whatever edge you add to them, whatever missing edge you add to them, we always make a triangle. So this graph is saturated, K23 and C5 are K5, K3 saturated. And regarding the saturation, graphs which are FH saturated, we are interested in the FH saturation number, which is defined as being the minimum number of edges of a graph, which is FH saturated. So this is one parameter that we study regarding saturation. And what would be then the weak saturation number? So on the weak saturation, we don't require that every edge needs to create a new copy of H. We just need that there exists an ordering of edges such that whenever we add this edge to the current graph, we always make a new copy of H to this graph. So we can see kind of the weak saturation as kind of a process that we start with a spanning subgraph of F, which is a spanning subgraph. And whenever we add an edge, this edge needs to make a copy of H, a new copy of H. And we can add all these edges until we have the full graph F. So basically here, so first of all, because we are kind of requiring less, we don't need every edge. So if every edge that we add just make a new copy of H, this graph is saturated, but it's also weak saturated because any permutation of the missing edges would also give, like, we will satisfy the conditions of weak saturation. So basically, K23, because it's K5 saturated, K5, K3 saturated, it will also be a weakly K5, K3 saturated. But notice that P5, it's not K5, K3 saturated because of this missing edge, this purple missing edge. If we add just this purple edge, will not make a triangle. But we can make an ordering of the missing edges. So for example, we can add all the edges between vertices of distance 2, and then vertices of distance 3, and then vertices of distance 4. And then we eventually have all the edges, and every edge that I said in this order will just make a triangle. So, and equally, analogous to the saturation number, we have the weak saturation number. So, and in this case, we are interested in the minimum number of edges of a graph G, which is weakly F saturated. So are we all happy with the definitions of saturation number? Okay, and weak saturation number? Okay, so the weak saturation, one more thing. It's just to simplify lots of times regarding whenever we are talking about the saturation or the weak saturation number, instead of whenever like the host graph is the complete graph, we just write as well like weak saturation, and instead of putting Kn, we just write N instead of Kn. This is a notational thing. Okay, so the weak saturation number was actually introduced by Bollobás in 1968 when he was actually trying to prove the saturation number of complete graphs. And for M between 3 and 7, he showed that the saturation number is equal to the weak saturation number, and it's equal to this formula. And he conjectured that this would hold for every M. And Bollobás in 1977, he showed that he proved this conjecture, but independent versions were also given by Allen, Frankel, and Calais. Each one of them gave independent versions. So once you have a problem and a parameter that you study for complete graphs, maybe the most natural thing would be, one way of generalizing would be, what about complete bipartite graphs? And surprisingly, not much it was known before this work. So Fodor-Gold and Jacobson in 2013, they studied weak saturation number for some graphs. And among these graphs, they show the weak saturation number of K23. But complete bipartite graphs were mostly studied regarding the weak saturation parameter whenever like the host graph was actually a complete bipartite graph, not actually in the case of the host graph being complete graph. So Moscovici and Shapira, this is not the only result in that paper of 2012, but they show the weak saturation number of KPQ and KNN. They determined this number, and it was actually built on the work of the saturation of Allen, that Allen did in 85. And the desaturation, it's kind of a weak saturation problem, but it's a labeled version in the sense that actually in here, you're looking for a K, like your solid graph H, it's all, in this case here is KST, and your host graph would be KLM. And actually what you require is that additionally to creating an edge, there is an ordering of the edges that whenever you add an edge, you make a new copy of KST. Now you are requiring that the S part stays in the L part and the T part stays in the M part. So it's kind of like labeled version of weak saturation. Yeah, so this was basically all the work that was known about complete bipartite graphs. Other parameter, like other graphs were studied in weak saturation number, like for example, weak saturation number of hypercubes in hypercubes, also weak saturation number in GNP, as well as being the host graph. Other graphs, like other graphs are also considered in the study of weak saturation. But in the focus of this talk will be complete graphs, complete bipartite graphs, and this is what we'll be talking next. So we'll be talking now about our result. One of our main results is to show the weak saturation number of KTT, and which is equal to T minus 1 times N minus T over 2 plus 1 for every N bigger or equal than 3T minus 3. So whenever we want to show the weak saturation number of a graph in a complete graph or in any other graph, what we need to do is prove the lower bound and the upper bound, the upper bound usually is the easy part because you just need to give a construction. So if you show a graph, which is to have this number of edges, and that there is an ordering of the edges that you add, and always make a copy of KTT, and at the end you obtain the complete graph, then you just show the upper bound. So in this case here, we have this graph, which is made of parts X, Y, and Z. The X part has T vertices and it's a KT. The Y part, and the Y and the Z part are independent sets. The Y part has T minus 1 vertices and the Z part has N minus 2T plus 1 vertices. So in total, we have N vertices. And we have all the, in here, we have between X and Y, we have all the edges. Between Y and Z, we have all the edges as well. So how would be the process? How I show that there exists an ordering of the missing edges that would just make the complete graph that we can add, and we always make a new copy of KTT. So first, we will show that we can add any edge of X between X and Z. So pick an edge of X and Z. Let's say that Z is part 1, okay? And let's say that this vertex is in X is of the part 2 of the KTT. All the other vertices in X, say that they are all together with this vertex of Z. So X is all the vertices are in part 1. So we have T minus 1 vertices in X and 1 vertex in Z being part 1 of the KTT. And now we pick this 1 vertex in X and all the vertices in Y to be part 2 of the KTT. So notice that part 1 is just between X, like all the vertices in X and 1 in Z. So all these vertices in Y, they are adjacent to X and Z, so they are fine. The other vertex in X, which is in part 2, let's say it's connected already to all the other vertices of part 1, except for the one in Z. So I can add, like this missing edge I can add, and I can have like all the edges between X and Z added in any order that I want actually. So all these edges can be added first. And next, I would have then that I have all these edges between X and Z already now, and I can add all edges in Z just by noticing that I just pick 1 vertex in Z to be part 2 and all the vertices in Y to be the part 2 of the KTT, and the other vertex in Z to be part 1 and all the vertex in X to be part 1, let's say. And then I have, because we kind of have a track, like all the edges between X and Z, so we are all fine. And then, because basically now we created a big complete graph. Actually now we have all the edges between X and Z. So we actually have a Kn minus T plus 1. So this complete graph is really big. And because of this condition, actually can just choose 2 vertices in Y, all the rest in X union Z, and you'll be fine. So with this, we just show that there is an ordering for this graph and how many edges this graph have. Well, this graph between X and Y, it has T times T minus 1 edges. Between Y and Z, we have T minus 1 times N minus 2T plus 1. And in the X bit, we have T choose 2. So we have this exactly the number that we want to show. So this is the upper bound. And now, so usually this is the easy part. So let's now try to show what would be the lower bound. To show the lower bound, usually the lower bound is the tricky bit, and it will require most of the work. And we will need this lemma of Bollobás, Morrison, Riordan that says that if you have a graph F, let F be a graph, W a vector space, and F is the set of all copies of F. Oh, sorry, I need to change this. Sorry, this is the node version. So this is the lemma that we actually, because I wanted to show you more generality. So the lemma, and which is actually quite nice, and the proof is short and cute, so and very nice. So we will just show the proof in here. So we are given graphs F and H, and we are given a W a vector space. So this graph F is our Kn, right? Is like the host graph. So for each edge, we will assign a vector inside the vector space, okay? And what we want is that every copy of H in F, which would mean every copy of KTT in the complete graph, if we look at the vectors related to the edges, there are non-zero scalars for that specific copy, such that we would show that there's this linear combination that would give us the zero vector. So if we have a vector space with these conditions on the edges of the vectors associated to the edges of F, then we actually have the Week's saturation number of the graph H in F is actually big or equal to the dimension of the space of the span of this of the vectors associated to the edges of the complete graph. So it seems complicated, but we will see that it's not. And the proof hopefully will help, but we also will translate this for exactly for our setting. So basically the idea is for this proof is that let's start with our weekly FH saturated graph. And let's consider this ordering of all the missing edges such that each edge that we add, it makes a new copy of H. So we just say that this copy is HI. So the condition here that every copy of F, we have this linear combination with non-zero scalars, implies that this vector, it's already in the span of the edges of HI without this edge, right? So if I just look, let's say for KTT and remove the new edge that I will add, it's already like the span of these vectors is already, these vectors are already contained in the span of it. But at the same time, HI is contained in this graph, which was defined as Fi, right? Which is just Fi, again, was just, whenever we see an edge that will make a copy of H, like regarding this ordering, we added this edge and make Fi, and then we add another edge and made Fi minus plus 1. So HI is a subgraph of Fi, which implies then that this edge, which was already in the span of HI, it's already also in the span of Fi. But notice that this is actually Fi minus 1, right? And this was Fi minus 1. So now what we have is that the span of the edges, of all the edges up to Fi minus 1, it's actually the span of all the edges up to Fi. Because Fi is just Fi minus 1 plus this new edge here, which are already in this span. So we have that the number of edges is actually bigger or equal than the dimension of like the initial the initial graph that we started, which is actually equal to the dimension of the graph that we end the process. So this is a very, very nice lemma because it actually gives a constructive way of showing the lower bound. Now, basically, you just need to give a construction and a construction of a vector space with this property, and then you are done, right? Like, and most of the proofs of weak saturation, they are always algebraic. We don't have like a proof of weak saturation number, which is only combinatorial. Yeah, so in this lemma, it kind of helps a lot in the sense that it kind of make it simple for us, although it's not that simple to find a nice set of vectors to satisfy this. Okay, so this is the lemma that we'll be using. Oh no. Okay, so I wrote here the lemma in terms of Kn. Okay, so this was the old version. I should have changed it. So here, now F was supposed to be H, the H that we were talking about all the time, and not F. Well, okay. So the weak saturation number, whenever this is H, so now this lemma in the KTT scenario, what we want is to assign vectors to the edges of the Kn, such that for every copy of KTT in Kn, we have that they are not linearly independent. And once we have this, we obtain that the weak saturation number of KTT in Kn is equal to the dimension of these edges.
May I ask a quick question?
Yes.
Is it enough to know that they're not linearly independent? I mean, for the proof, you also need the coefficients to be non-zero in this linear combination, all of them to be non-zero in the linear combination, right?
Yeah, yes. Let me wait a second. Yeah, yes. So this is, yeah, I was just trying to short, but it's not. Yeah, you're right. So again, see, put a cat in here. Yeah, exactly. So you want just that. Whenever you see a copy of KTT, we actually have that there are non-zero scalars that we have like that copy, a linear combination that gives zero, and they are non-zero, each scalar. So we will obtain this. And this is what we want. Okay, so we will like now. So one more thing is that actually to just assign vectors, it's not a difficult thing satisfying this condition that every KTT, the right condition here. The problem is we could assign, for example, every edge the same vector. But the problem here is that we need to satisfy, we have to this trade-off that we need to satisfy this this condition for all the copies of KTT, but we need to have like a big dimension, otherwise this is like useless. So this is so now we will see how we assign these vectors. So now we would do this for the case where t equals 3, which means that we are looking for K33. So we are determining vectors of the edges of the complete graph in such a way, again, that there's no linear combination that takes to the zero vector with the constants not being zero. Not being zero, no, sorry. With they all not being zero, yeah. So let's see here. So how do we do this? So in the case of K through 3, what we do is that, first of all, we'll consider vectors for each vertex. So for each vertex, we will assign a vector in R2. And this 2 is because 2 is 3 minus 1. Okay, so if it was in the general case, it would be t minus 1. And we want, in a way, that they are kind of minimally dependent, which is that any two vectors, they are always independent. So whenever I pick this, so for example, we could just pick vectors in general position with high probability they would satisfy this. But another example would be kind of considering powers, let's say like this, like of, for example. So, and how we will define our vector for each edge. So for each edge, we will assign this vector, which is this product, where, let's say for the ith entry, we actually, between the edge Fij, we put in the ith entry the vector associated with the vertex j, and the jth entry, the vertex associated with Fi, and all the rest, we'll just put the zero vector in R2 in this case. And so this is the vectors that were associated to each edge of Kn. And why this is nice? Well, they have this key property that whenever we have a linear combination that gives 0, we actually have 0 in each entry associated to this. And actually, we will also see that if we pick just a bunch of vectors, let's say let's say that we are considering a subgraph of our graph, if we kind of look through the point of view of vertex, we will actually see all the neighbors of the vertex. So if in the ith entry, if we are just considering the edges of the subgraph, we will just see the vectors associated to the vertices which are neighbors of the ith vertex. Yes. So let's show now. So this is how we define our vectors associated to each edge. The vector space is just the space spanned by these vectors. Okay, and now we need to show, first of all, that we actually, for any copy of KTT, we have, they are not, we have like a combination. We can always produce the zero vector, a linear combination where the constants are not 0 and all non-zero. So this table, so in here we have K33. I just put names to the vertices to simplify. And in here we are actually looking at the edges. So EA1 is just the edge A1, and this is actually the vector associated to the edge. So we are kind of looking at the 8th entry, the bth entry, the cth entry, the 1th entry, the 2th entry of the vector EA1. So hopefully everyone can understand this. So how will we find these constants? Well, let's first, because we chose the vectors for each vertex, being like F1, F2, F3, Fa, in a way, that they are minimally dependent. Actually, they are in R2. So any three of them, there exists an alpha and beta different than 0. And because we chose them being any two of them are independent, so there exists alpha and beta different than 0, such that we have this property here, right? The f1 plus alpha 2 plus beta 3 is equal to 0. So we have this. So we can just, and in this first column, we're actually trying to build the constants that will kind of associate it to each vector. And we want to kind of make every column to be equal to 0. So notice that if we just choose this alpha and beta satisfying this, so now the 8th entry of all these vectors we are happy with, if the constants were this. The bth entry as well and the cth entry as well. But fa, fb, and fc, they also are three vectors in R2, and they also have this property that they are, any two of them are independent. So there exists k, l, and mu different than 0, such that we have this linear combination of them being equal to 0. So now what this means is, let's just multiply everything by k, this first. So for example, this new constant will be like from of the edge EA1 will be just k, of the edge A2 would be k times alpha, the edge A3 will be k times beta. So these are the constants. And because for A1, AB1, and AC1, they are like K, L, and mu, we have that this will be equal to 0, this bit here. And notice that whenever I did this, it didn't affect actually the 8th entry, the B entry, and the C entry, right? Because I just had F1, F2, F3, in this case, they're all multiplying. They just have K in common, so they're just multiplying. So in here, the same as we did it with A, B entry, and C entry that didn't change. Actually, if we just look at the 2th entry and the 3rd entry, what we see is that we have alpha multiplying all this same linear combination and beta multiplying the same linear combination. So with this, we just show that if we just multiply every one of these edges by these constants, we'll just obtain the 0 vector. Let me see the time. Okay. Yes, so now we are kind of almost happy. We just need to finish this. We need to calculate the dimension of this space. And okay, so we are in the K33 case. Our construction, we will use the same construction that we did for the upper bound, which would be, remember it was, in this case, would be like, this would be, I think was X part, Z part. The Z part was just in this right part, but I just put it in the top now. And we have a KT in this bit here. So this is just the construction for the K33. And now what we want to show, it's actually that all these vectors, they are linearly independent. So if we can show that they are all linearly independent, we are done. So let's consider a linear combination that gives the 0 vector. And remember that because the way that we construct the vectors, we can kind of, to guarantee, I think I put it here. Yeah, because we construct it in this way, we can actually look kind of trying to always look for each entry related to a vector, make sure that we are kind of having the 0 entry there. So because this linear combination gives 0, it will give 0 if we look at one particular part. The same combination will be 0 in one particular vertex if we look at it. So notice that W1 and W up to Wn minus 5, which means all the Z part, it was before was like T minus 1 on top and lots of N minus 2T plus 1, I don't know, connected to this T minus 1. And they all have degree T minus 1, which is in this case is just 2. And because they are always minimally dependent, which means that any two of them are independent, it implies that all these edges, if there is a linear combination which gives the 0 vector, all these edges need to have coefficients in the linear combination, which is 0. So we have that this is 0. So now, actually, we just need to show that these vectors are linearly independent. And to show this, it's a lot of work. And I will not do this here. You can read the paper. But yeah, this is basically the idea. So now we have a finite number of vectors to check they are linearly independent. And we just need to find a nice order to kind of conclude that, oh, this constant needs to be 0, this constant needs to be 0, and so on. And this is how we do it. Okay, and so now we just show the weak saturation number of KTT. To show the KT as a corollary, we have the weak saturation number of KTT plus 1. And how do we just prove this? Well, because KTT plus 1 is just a subgraph, KTT is a subgraph of KTT plus 1, we already have that the weak saturation number of KTT plus 1 will be at least 1 unit bigger than the KTT, right? Because I could just, if it was the same, let's say, I just pick the KTT graph, the KTT plus 1 weak saturated graph, remove one edge from one copy of KTT, because if it is missing one edge, will be like a copy, it will have a copy of KTT. So I just delete this edge, and then this will be a weak saturation, a weak saturated graph of KTT. Yes, so we already have this, and now we just give the construction, and the construction was the same as before, but actually you just need to add this new vertex, and everything will be nice and fine. So this is the corollary, and for, actually we're supposed to have a pause in here, but it's fine. So if we are talking about complete bipartite graphs in general, and if you think about lower bounds, not much was known previously to our work. So the only lower bound was actually the trivial lower bound, which will be for any, if you are looking at weak saturation number of any graphs F and H, actually, if you just look at the minimum degree of the graph that you want to find copies of it, you just need to, every vertex needs to have like the minimum degree at least the minimum degree minus 1. Otherwise, you cannot never add an edge. So this would be the trivial lower bound, because in this case here, we're considering that S is less or equal T. So every vertex needs to have degree s minus 1 at least. So you would have at least this many edges. And what we show, it's actually that the weak saturation number is, we determine asymptotically the result, but so we showed that the weak saturation number of KST is equal n times s minus 1 plus a constant which depends only on s and t. So we have a gap in here on the lower bound construction and the upper bound, but it doesn't grow with n. So for the upper bound, we have.
So sorry, can I ask another question?
Uh-huh.
So when you say this, that it's equal to n times s minus 1 plus a constant depending on s and t, you mean that there are like two constants depending on s and t, and it's at least n times n minus 1 plus the first, but at most n times n minus 1 plus the second? Or is it literally equal? Like there is a particular constant independent of n such that this is equal to...
No. Yeah, we don't know. So, but actually, yeah, what I mean here is that there are two constants, and it's in this sense that it's asymptotic in this sense, because we have a constant for the lower bound and a constant for the upper bound, and they match, I think, only in the case of t s being t minus 1. Apart from this, we don't have it, and actually we believe that our lower bound, it could even get improved probably. So yeah, so we don't know.
Thanks.
In this, maybe, yeah, okay, but yeah, maybe we actually don't have like much of a feeling, because for S and T, it's actually depending on how big a S is compared to T, it seems like one way, and then if it gets much bigger, it seems like a different way. So we don't have actually like a feeling of how the general structure should look like, because yeah, if S and T, they like have different orders, usually it's another construction, like it's different construction. Yeah, but maybe there's something in general, we don't know. Yeah, so the upper bound, this is the construction. There we have. Yeah, I don't want to enter in details on how you can make this a complete graph, but you just notice that there is an order of the edges that you can add them, making copies of KTT, and eventually you have the complete graph. And this is one graph. For the lower bound, which usually is the tricky part, but because we actually think that the lower bound could be improved, so it's not so tricky, because yeah, it's a more simple lower bound. What we actually do is that start with a graph G, which is weakly KST saturated, and it has the right number of edges, which means the minimum number of edges. And then just consider the graph G prime, where we added an independent set of T minus S vertices, and we put it all the edges between this graph G and this independent set. So notice now that this graph is actually KTT saturated for this and for this new number of vertices, exactly because this was KST. And now whenever the S bit here, you were looking at a copy missing an edge, just put this SC together with this T minus S part, run the process here in G, then you have the complete graph in G, and G is big enough. So we just add all the vertices, all the edges between this independent set. So with this, what we have in here now is actually the Dirac saturation number of KST and KN plus this number of edges that we added is equal the Dirac saturation number of KTT on this complete graph, right? And then we just obtain exactly this lower bound. So yeah, so this lower bound is simple, but we didn't have to do something much deeper to find to match this the upper bound in the asymptotic case. But if you want to do something better for other values, you probably need to, like, it doesn't seem that you need to add all these edges. It's a lot of edges, and we believe that actually you don't need to add that many edges. Maybe if you are clever and you add just less edges or to a specific bit, like, or something like this, you can make some argument that you could potentially use less edges and have a better lower bound. And some observations are this lower bound matches the upper bound when s equals t minus 1. And this is just another way of also giving the kt t plus 1 result. If we actually look, substitute this for t minus 1, actually you just get the kt t plus 1 result as well in the lower bound and the upper bound that we gave. And this upper bound and lower bound, they differ by this. So this is exactly why they differ. Yes. So now we actually are reaching the end of the talk. I hopefully I was not too fast. Let's see. Okay. So open problems. There are many weak saturation problems which are open. Not only for complete bipartite graphs, but for many other. Like I said, there is literature for lots of problems on weak saturation. But in the complete bipartite case, even like for r minus s bigger than 1, it's kind of open. Even if you just consider 2 and something bigger than at least 6, and this would be open. So we actually don't have a good idea of KST or KRS or anything like this. If you consider if you represent the complete multipartite graph, where we have k parts and each part of size t, actually our construction for the KTT generalizes, and we have this construction that actually it's an upper bound. So if you just consider, basically what you're seeing here is kind of like a copy of this graph where one of the parts has one vertex less than what you're supposed to. One part of size t has actually a kt inside, and all the other vertices are adjacent to these parts except for the part of the kt. So kind of this is the construction, and we wonder if this is the best possible for this case, which would be nice and would also kind of give let's say the equivalent results for the complete multipartite case where each part has the same size. And just to kind of motivate this for you to believe that it probably is the right thing, actually, if you consider the complete graph being any partite graph with each part having size 1, this is exactly the construction that gives the weak saturation number for the complete graph. So this is one question that I would be really interested in someone solving it. And in general, we can even ask, okay, so maybe the parts have different sizes, which would be the generalization of KST, right? What can we say in this case? Yeah, so this would be another upper problem, and this is it. Thank you very much.
Thank you very much, Taísa. Let us all thank the speaker. Are there any questions?
I have a question. So in your linear algebra part of the proof, did the arguments depend at all on the field that you were working in, or does it work over arbitrary fields?
I think it works for arbitrary fields. Yeah, I don't think we use anything specific.
Yeah, because I was wondering, because it seems like the arguments seem very natural to phrase in terms of matroids. Actually,
of what? Sorry, natural in terms of. Oh.
I was wondering if any of these works have been generalized into the matroid setting.
I have no idea. Yeah, I don't know.
Yeah, it sounded like that to me as well, actually. It's I had the same question. It's like, right, you're looking for a matroid whose, I guess, circuits has some kind of property in how they interact with the copies of the graph that you're looking for inside of KN.
I never thought about it, but nice. Yeah, I don't know, to be honest.
I was also wondering, is there something similar that people look at for in hypergraph settings, like three uniform hypergraphs?
Yes, there is weak saturation number on hypergraphs as well. Actually, the work that I said they were actually of Moshkovich and Shapira, they are actually doing kind of the analogous bit saturation and also working with weak saturation number, but in the hypergraph setting. Yes.
Yeah, you can imagine that your approach can tell you something about like three uniform, three-partite, complete three-partite hypergraphs or something, right? Maybe.
Maybe. I would need to think about it. Yeah, we didn't thought about hypergraphs. We know that they exist. We try to really try to generalize for the, let's say, KTT, but then KTT is not that simple anymore because they need to kind of like the KT2, they have like this really nice, we would need a new set of vectors, or maybe not even vectors, but like, for example, Angie has this proof also with polynomials. So we thought about it, but yeah, for vectors, for example, we couldn't think of nice vectors that would give some structure, like easy to kind of associate it with the copies.
Yes, that's why I said three uniform hypergraphs or something like this. You can at least imagine that you want, like, for every hyperedge, You want to have like, at each vertex, you have take some kind of mixture of the other two things related to the other two vertices. Do kind of something analogous to this, and we hope that it works.
Yeah, I will think about it. Yeah, I think would be probably more hopeful than maybe KTT. Maybe the 3 uniform. It makes more sense.
Are there any other questions? If there are no more questions, let us thank the speaker again. And our speaker next week will be Andrew Treglon from University of Birmingham.